Okay, so we're going to talk about magnetic force. A magnetic force is force. You put it. We talked about this last time. You put a charge in an electric field. You feel an electric force. You feel mass in the gravitational field. You feel a gravitational force. You put an object that has a pole in a magnetic field, and it feels a force. Now, there is another way to feel a force using magnetism. We talked a little bit about it. What was it again? Do you guys remember? Something else feels? What? Yes, solenoid. So that's the backwards of what I'm talking about. Solenoid is, I'll say it after you guys tell me what the answer. So a charge on its own is stationary. Does it feel a magnetic force? No. So what needs to be going on with the charge? Charge needs to be moving. The charge that's moving generates a magnetic force, and the solenoid is the other way around. It's a magnet that causes the reciprocal energy. Exactly that. The charge is to be moving, and a moving charge, in your terms, is called a current. All right, so we're going to talk about that. So we're going to use these rules, and you'll use your right hand, and in some cases your left hand, and I'll try to come up with some interesting mnemonics on how to remember which is which. In the second part of today's class, we're going to talk about mass spectroscopy. Mass spectroscopy is a tool that you use in academic labs or even industrial labs, where you determine the mass of substances. The way we figured out the mass of all of these guys in the periodic table is we use a machine called a mass spectrometer. I'll show you guys how it works, and it's really, really quick. Now, so we said a moving charge generates a magnetic force if it's inside of a magnetic field. Okay, so a charge moving in a magnetic field creates a force. So that's three things that are very, very, very important. So here we go. We have the force, which we're going to call FB, magnetic force. And that is of a relationship between the charge, that's a Q, not a G, the charge, and that's a comma, because I'm not going to give you the relationship yet. The magnetic force, the magnetic field, not the magnetic field, and the direction in which the charge is moving, the velocity vector. Okay? So a charge that has a velocity v that travels in a magnetic field will have a magnetic force. We'll feel a magnetic force. We'll talk about that. So those are the three parts of your right-hand rule that we're going to use, and everyone's going to try to do this together. All right. So the way it works is you're going to point your thumb in the direction that the electron is moving. You're going to point your fingers in the direction of the magnetic field, and your palm is going to point towards the force. Okay? So, let me do some examples. Actually, right before I do that, I'm just going to explain this real quick to you. Because we're dealing with things in 3 dimensions now, and you guys are kind of familiar with that if you've done linear algebra. I would put vectors in 3 dimensions. Stuff that you might be familiar with. But just for convention's sake, this here is the symbol of a vector coming towards you. Coming upwards towards you. Because I have to use this 3-dimensional aspect, right? So it's coming towards you. That's how you draw this. This one, the vector is going into the page. Okay, so towards you, away from you. And the way I like to remember that is if you were to look at an arrow, when the arrow is coming towards you, what do you see? And when the arrow is going away from you, what do you see? An arrow, like a bow and arrow. An arrow, when it's coming towards you, you just see the pointed end coming towards you. When an arrow is going away from you, you see the feathers at the back of the arrow, and you can see it going away. That's the way I remember it. And that's how you would draw a vector, not just magnetic field, but any vector. That's how you would draw a vector going inside into the page or coming out of the page. Right? We're going to need to do that. And so here we're going to use the right-hand rule. Just a big disclaimer. I'll do it after, actually. Let's do this first. So here what we would do is we would put our thumb in the velocity direction and point our fingers into or out of the board, into or out of the board based on this drawing. Is it coming out or going in? Coming out. So thumb towards that way, and make sure you use your right hand. Fingers coming out. Where is my palm pointing? My palm is pointing down. So in this case, I can say that the force vector is pointing downwards. So here we go. FB pointing downwards. What's that relation? What's that mathematical relationship between these vectors? What's the term that you might have learned in orthogonal is a term, but the mathematical algorithm that you use, not dot product. Okay. Normal. It's the cross force is the cross product of velocity and the magnetic field. Okay. Real quick though. Okay, so this part you have to stretch your imagination. When you have an object that has a velocity that is tangent to the force, what kind of motion is the particle going to have? So again, remember, the velocity is tangent to the force. What kind of motion does that create? Okay? So problem, do you think it's going to go like this? What else? That's a good answer, not the right one. Let me ask you another question. All right. After a small moment of time, all right, because of what, as Al said, is true, its acceleration is downward. So therefore, the particle is going to be over here, and it's going to have a velocity vector in that direction, right? Because this is going to be that. Okay. Where is the force vector pointing to now? You're going to have to use your right hand rule again. So thumb in the downward direction. So it's going to be pointing somewhere along here. So now the force is in that direction. And if the object is over here, or even better, if the object is over here, the velocity is downwards. In which direction is the force? Towards the left. Exactly. Like this. So what kind of motion is that? Circular motion. All right. So in fact, this force that you're getting, right? So it's FB all the time. When you have it in this case, FB is going to be equal to, what's the force called that keeps an object in circular motion? FC, C stands for centripetal, not angular momentum, centripetal force. So FC. So this object is actually going to go like this. So my charged particle is going to make a full rotational motion. It's going to go on and go on and go on. Okay. What is the formula for centripetal force again? Did you learn centripetal force? Yeah. Okay. Is equal to mv squared over r. I saw Mr. Wakarsky on Friday actually. He says hi. Yeah. He's in between trips. He's like my idol because he went to Japan, Taiwan, and the Philippines with his wife and daughter, Then his wife and daughter flew back, and he himself flew to Kazakhstan and some other countries in Central Asia. And then from there, took a train to Europe, and then was just shopping for cheap plane flights to fly around and see wherever he can, and end up in a place that could fly him back cheap to Montreal. Now he's here, and he is 10 days wait so that he can get on his next flight and go to South America. Crazy. Okay, if I'm looking at this formula for centripetal force, v represents the velocity that the object has. It has the same velocity all around. All right, I'm talking about the magnitude of velocity. Its direction is changing, but its velocity, its magnitude is not changing. Okay, so the velocity is the same all around. Mass is the mass of the particle here. So this object is going to have a mass m, and r represents the radius of this circular motion. Okay, so r is the radius of this circular motion. So far, so good? Yeah. So then what happens? What would the cross product be? 0. No force. Can you guys figure out the direction of the force here? Oh, no, wait. Here the force is given. The electric field is given. It's asking you to find the velocity, the direction of the motion. All right? So now your palm is going to be pointing towards where? Toward the left. All right? So your palm is pointing towards the left. Your fingers are pointing into the paper or out of the paper? Into the paper. So which way is your thumb pointing? So again, look, my palm My thumb is facing there. My fingers are into the paper. Where's my thumb? Up. Okay. So in this case, my velocity, this particle would be going upwards. Nope, not V, not F, but V. Okay. Now, that's great, fine and dandy, except you use your right hand for positive charges, you use your left hand for negative charges. You think you'll remember that? So here's my way of remembering it. Who here is in organic chemistry? Okay, a fair bit of you. Those of you in organic chemistry, you know that there is chirality, right? There's plus chirality and minus chirality. So those terms, the plus and minus, have we call them right-handed rotation and left-handed rotation. And plus is right-handed rotation because it turns clockwise, and minus is left-handed rotation because it turns counterclockwise. That's the way I would remember it, and that's because I studied biochemistry and organic chemistry was shoved into my face for it. But another way of remembering it, so Lee, Kim, and I were sitting in our office. We're just joking around about what possible way we can think of to make it funny. And so we came up with another funny way. Not that the organic chemistry was funny, but anyways, if you were to use your left hand, you would see the letter L because you're a loser, and that's negative. But if you use your right hand, other people are losers, and that's positive somehow. Yeah. Okay. Anyways, either way, just remember that right hand is positive and left hand is negative. Yeah, that's what we do in the office. That and eat chocolate. Okay. So for these examples, I want you guys to solve for the force. Use your right hand. All of these are going to be positive charge particles. Okay. You guys do it. I'm just watching you do it. That's the point of this, so that you can remember. I don't see a lot of right hands. Huh? The X's? So for the letter B or for the magnetic field B? The force is going into the page, yeah. X, yeah. Go on. Yeah. B is magnetic. The variable B, capital B, is magnetic field. F sub B is magnetic force. Gabriel, you're using your right hand, right? It's the right hand rule. So you're doing the opposite of what your left hand is. I didn't hear what you said. All I heard was Targaryen symbol. Oh yeah, that'd be really cool. Okay. Theme song. You'll play the Reigns of Castamere on that. You'd have to have another picture of like blood just leaking out of you. Did you guys get these answers? Yeah? Hopefully. If you have questions, now is your time to speak. Yeah. D, yeah, absolutely. So thumb is for the right, fingers towards you, so I always go like this. So my palm is pointing. Okay. Based on what we know, we can figure out that these objects undergo circular motion. Right? So we have their instantaneous velocity, and their forces is tangential to their velocity, which makes them go in circular motion. Now, based on that idea, which one of these would be true? So you have to imagine that this here, this particle here, is being submitted to a force that's, if it's going into circular motion, that means the force is always towards the center of the circular motion, right? So the force is always going to be in that direction. So which one of these situations represents a negatively charged particle? So you guys get. So which one of these is right hand rule? Which one of these is left hand rule? Okay, what's the answer? Tommy? A and C. A and C. Good answer. So those ones will submit to the left hand rule. All right, so here's what I had said before, that an object that's being subject to a magnetic field that's perpendicular to the movement of the object is going to undergo a circular motion because of centripetal force. Okay, that's what is written here, and we've learned a little bit about that. You need to remember that the what do you call it? The equation is equal to mv squared over r. Okay, but that's written in the slide before. All right, so now here is the actual mathematical relationship as you may have seen it in linear algebra. I'm sorry for having to drag math into this course, but that's the nature of physics. Math is at the heart of it all. So it's the cross product of the velocity vector with the magnetic field vector. Okay, and you guys know what a cross product is, right? I hope so. And in order to find the magnitude of the cross product, I've also set up this equation just here underneath it. That is, Q is equal to, the force of the magnetic field is equal to the charge, the magnitude of the charge, so whether it's positive or negative and it's charged in coulombs, multiplied by the magnitude of the velocity vector, multiplied by the magnitude of the magnetic field vector, and then multiplied by the sine of the angle that separates them. All right. So, for example, I have my velocity vector v, and my magnetic field vector b, right? My force vector is going to be perpendicular to both. Okay, you guys have seen this kind of drawing in your linear class, all right? Even if v and b are not perpendicular to each other, right? The force vector will be perpendicular to both. Okay, by default. All right. Now the what do you call it? The magnitude of that normal vector, the magnitude of FB in this case, is dependent on the angle between the two. So this angle here, we're going to call that angle theta, all right? And the bigger that angle, the closer it is to 90, the bigger the magnitude for magnetic force, all right? So if you have V and B going in the same direction, right, it would be 0 degrees difference, and the sine of 0 is 0, and so therefore your force would be equal to 0. Now you would maximize the force if the angle between the velocity and the magnetic field vector are 90 degrees. That's the maximum. Yeah. No, for magnitude. Okay. Now, Lee and I, we might do some kind of joint assignment, but I won't ask you guys to, only in my course, to do a cross product vector matrix, whatever. Um, I'll let Lee test you guys on that. We might do like a joint thing. That would be kind of cool, I think. And for me, you need to just know that you need to apply this basically and determine the magnetic field, the magnetic force based on the angle between these steps. So far, so good? Yeah. So what's the difference between electric field and magnetic field? What have you noticed? Tell me what you remember about electric field and what you might apply now in magnetic field. What do you think? Okay, so not maybe not linear trajectory because we can make them have parabolic trajectory, but I like what you said about the trajectory of the particle is in the same direction as the or the initial direction of the particle is in the same direction as the electric field. So we're going here for electric field, we're going to say that acceleration is along the same plane as E. And for magnetic field, you can say that the acceleration, that's not how you spell acceleration, the acceleration is perpendicular to the field vector B. So this will cause an object to go in circular motion, and this one is either going to be linear if it's in the same direction or parabolic. So I'm going to write both, so you guys should know. Oh, I have them opposite, eh? This is going to be linear or parabolic, and this one is going to be circular, circular motion. Oh, sorry, I didn't know it switched. Sometimes when I just put a dot at the end of my sentence, it switches slides. Yeah, Kevin. Yeah. All right. I should wait a couple more seconds. So how do you generate a magnetic field again? Yeah. Moving charges, you can generate a magnetic field, or magnets. Yeah, magnets. All right, let's solve some problems. Remember that magnetic field is measured in the unit Tesla. All right, so you're gonna have an example of that here. This is just a very simple arithmetic using those, using the equation that we just saw. What you need to remember, however, and make sure you don't fall for this trap, is always look in the problem to see if we're talking about a positive charge or a negative charge. Okay? So read the questions carefully. Other than that, everything in this case is very simple and straightforward. So we're talking here about magnetic field, electric field, and gravitational field. Talking about magnetic field, the magnetic field is northwards, and the velocity is eastwards. And we have a negative charge. The electric field is, in this case, downwards, and it's a negative charge. And the gravitational field, well, that one's really easy. It's always downwards, and the object has a mass m. So I'm not done yet. I just drew the field vectors and the objects in the field vectors. You still have to tell me what the forces are, or which direction the forces are. So it's very, very, very hard to determine, it's very hard to draw your 4 cardinal points on a 2-dimensional piece of paper. So don't fall into the trap that north is the same thing as up. Okay? North is not the same thing as up. Who lives in the South Shore? Which way is home? The north would be that way, yeah. If you're just want to use real coordinates, north would be that way, not that way. So could you tell me about the magnetic field and which direction is it? In my drawing, is it into the page, out of the page, up, down, left, right? It can't be in the same direction as magnetic field. I'm asking for the magnetic force, yeah. So use your right hand. Velocity is going to be towards the right. Oh wait, it's an electron. Left hand. All right, so velocity, velocity is to the right. Magnetic field is towards the north, and the north is there, over there. And therefore, which direction is magnetic field? Downward. Right? So it's going to be, in my drawing, it's going to be into the page. Okay, and that is representing downward direction, downward. Yeah. The vector, yeah, so vector is going that way. My magnetic field is going up, and therefore my magnetic force is going into the paper. Yeah, but what's that? But downward is into the paper. What you have to remember is I'm looking at my cardinal points as if I'm looking at a map, where north is the opposite part. If this was a map, right, and I drew my cardinal points, north is that way, east is that way, and downwards is that way, closer to the planet. All right, so that should say downward, not downward. Downward. Electric field is pointing downwards. That's a downward direction. And it's an electron. What does an electron do in an electric field? Goes in the same direction or opposite direction? Opposite direction. So in this case, my electron is going to be feeling an electrostatic force going upwards. All right, so it's going to be upwards. And gravitational field, that one's always easy, right? Is anything going to float away from the planet? No, anything that has an object, any object that has a mass is going to go down. You know how an object has a charge, either positive or negative, and it does different things in a magnetic field. And an object can be charged positive or negative and do different things in a electric field. A mass, what is the alter ego of mass that'll behave differently from the mass that you guys know it? So I have matter and antimatter. So antimatter will behave it's like the negative charge of mass, and so that'll behave a little bit differently in a gravitational field. Okay, and calculating this is really easy. I'm not going to do it, but I want you guys to. Is here the force is going to be equal to QVB, and because their angle is 90 degrees, I don't need to do sine theta. Here it's easy. It's QE, right? So F is going to be equal to QE. And then here is also easy. It's F is equal to mg. Those are how you calculate each of the three different forces. That makes sense? Yeah. So I'm looking, the question is asking about the force. If you're looking for the force, you have to use the force is equal to Q times V times B. And there theoretically, what happened there? Theoretically, there should be a sine theta, but the